Hello and welcome to this video on Wi-Fi. No configuration in this video. This is part of the theoretical background video series, and I would like in this video to answer a question I often get when people look in detail into 802.11ac, and that question is, why is it that there are some MCSs that are missing? What I mean is, when you look at 802.11ac in detail and you look at those tables of VHT MCSs in the protocol itself or anywhere in the internet when they talk about these MCSs, you see that some of them are labeled not valid. And the question I get often is, why? Why are these not valid? What's wrong with those? So this is what I would like to share with you today. This video is a little bit on the complex side, so I'm going to assume that you have a basic understanding of OFDM, BPSK, QPSK, at least that you know that BPSK is changing the wave direction to mean 1 bit, QPSK is changing the wave direction to mean 2 bits at a time, then QAM is going to shoot signals with different intensity and angle to mean a certain series of bits. If you have no idea about BPSK, QPSK, and QAM, you may want to look around for some other videos or resources to get a bit comfortable with those concepts before coming back to this video. And the reason is because to understand why these MCSs were labeled as not valid, we'll need to look a little bit deeper into the transmission mechanism of 802.11, and this in turn, beyond the 802.11ac protocol, may help you understand more in depth on how we send signals and bits into 802.11. The current list of non-valid MCSs is the one you see on this table, but actually it didn't happen that way. There were many more at the beginning. And to understand what happens, we need to go step by step into the transmission process. First of all, remember that OFDM uses what we call forward error correction, FEC. What that means is that when you want to send a series of bits, you're going to actually send more than this series. And the idea is that if you lose some of the sequence you send, the remaining bits around are going to be enough to help you understand what was supposed to be sent. This is what we call the repeat rate, the redundancy rate. The name changes depending on what angle you take. But the process is the same. So for example, if I'm using a rate of 3/4 or 3/4, this means that I'm going for 3 bits of useful data to actually send a sequence of 4 bits. And the interest is that if I lose some of these 4 bits, the remaining bits are going to help me know what bits are missing. So with these 4 bits, I can lose 1 bit and sometimes 2, and still be able to recombine the remaining bits to understand what sequence was supposed to be sent. So that makes it transmission resistant to interferences, and we send this redundancy even before we know what interferences we might be facing on the channel, and this is why it's called forward error correction. We correct the error even before it happens. So when you look at a table of 802.11 data rates, typically you will see the modulation being used, 16 QAM, etc., and then the rates, 3/4, 1/2, etc. So how does it work? Suppose that you have to send a series of bits, like the ones you have on the left here. The first thing you're going to do is to send those series of bits into what we call the scrambler. The scrambler has nothing to do with the problem we talk about here, but it's there, so let's look at what it does. Its job is to make sure that you don't have a long series of zeros or ones next to each other, because if you have that, it may be confusing for the receiver to understand if there is a change or if there is a long silence, etc. So we don't like to have too many zeros and ones one behind the other. So the scrambler is just a mathematical equation that is applied to those series of zeros and ones to make sure that the result is not too many zeros or too many ones in a row. It's called an XOR operation, basically, where if you have too many zeros, one of them will become a 1. If you have too many ones, one will become 0, etc. Alright, so no big deal. You take your data, but you send it through the scrambler. No influence on the MCS issue, but it's there. Then, if you take, for example, a rate, so a QAM, for example, 3/4, you're going to group your bits in series of 3, and because you use this 3/4 rate, you're going to send 4 bits for each series of 3 real data bits. So that's going to be called the encoded bits versus the data bits. So for 3 data bits, I'm going to encode, in fact, 4 bits because I will add 1 more bit to a series of 3, so I can lose some bits in that sequence of 4 and still understand what the sequence of 4 were supposed to be. So you see on the slide, I'm chopping my resulting sequence into series of 3 bits, and for each of the 3 bits there is an equation that determines what the 4th bit is supposed to be, And that makes that when I have this sequence here, I can lose 1 bit or 2 bits and still be able to recombine what the series of 4 was expected to be. So now I have 4 bits that I'm going to send for each real 3 bits of data. Thus the name encoded bits versus data bits. I have 3 bits, but I'm going to encode 4 bits because of the redundancy. Then the next thing that happens is that I'm going to take all these bits and I'm going to send them through a wave. So this can be using different techniques. BPSK is going to send 1 bit at a time. QPSK is going to send 2 bits at a time because each change of the wave represents a 2-bit change. And then the various versions of QAM, 16 QAM, 64 QAM, 256 QAM, are going to group these bits into larger sequences, and each change of the wave is going to represent even more bits than BPSK or QPSK. So in this example, I'm just looking at QPSK to make it simple. So I'm going to change my wave to represent 2 bits. So I'm going to group my bits into groups of 2, and each group of 2 is going to represent 1 change of my wave when I send my wave out. The last thing you need to know is what we call the symbol. The symbol is basically the duration of the useful transmission. In other words, my wave is going to travel at speed of light, and I'm going for a certain amount of time to make variations in the angle of my wave to represent those series of bits. Again, QPSK, every change is 2 bits, for example. I'm not going to do this forever because I'm expecting that my signal may be echoing somewhere on the wall and maybe coming back at me, so there may be some noise coming back from my own emission. So the way 802.11.FDM works is that you send for a certain amount of time, which is by the protocol set to 3.2 microseconds. And then you're going to not send anything useful for a certain amount of time just to let the echo come back on your wave. And that amount of time is called the guard interval, and it's by default 800 nanoseconds, but it can be reduced in 11N and 11AC to half of that, 400 nanoseconds. So 3.2 microseconds of useful signal, then 800 nanoseconds of non-useful signal, that's 4 microseconds, and then you start again, 3.2 of useful, you stay quiet for 800, etc. So I say you stay quiet, but in fact in the guard interval, these 800 nanoseconds, you still send traffic because radios can't really stay silent for that duration of time, but you don't send anything useful. Basically, you just repeat by anticipation part of what you're going to send next, but that's not a part of the wave that is considered by the receiver as being bearing data. It's just, noise that you keep sending to keep the radio busy during this echo thing. So the reason why we care about this symbol duration is because the result is that when you look at the protocol, the way we look at it is to say, per each symbol, per each period of 3.2 microseconds during which you're going to send useful data, how many bits of real data are you going to be able to squeeze in that duration, in that time of the transmission? And that's the way we look at the different modulations techniques. So if you look at the table at the bottom, for example, on the first row, you see that BPSK, which is going to change direction to mean 1 bit every time, can actually change direction 52 times per period of 3.2 microseconds. So 52 times the wave is going to change, meaning a different bit. That's the amount of change that you can squeeze into a 3.2 microseconds transmission with that kind of technology. So because this BPSK in this example is using a rate of 1/2, we are basically doubling the number of bits we send. So for every real bit of data, we're going to send actually 2 bits in the wave so that we can lose every half of them and still understand what is being sent. So this is why we say the coded bits is 52. You're sending 52 changes in your wave during the 3.2 microseconds, but because half of them are repeats of the previous, the real data bits that you are squeezing into that 3.2 microsecond duration is in fact 26 bits. So of course it gets a bit more complex as you go through more complex modulations, and that's why you see, for example, at the bottom, we say if you're looking at 64 QAM on an 80 MHz wide transmission with 6 special streams, the duration of the symbol is still 3.2 microseconds. So how many bits can you squeeze in 3.2 microseconds duration if you use 6 streams, 80 MHz and 64 QAM? Well, you're going to send 8,424 bits worth of information, but because your repeat rate is 2/3, 1/3 of these bits are going to be actually redundant, adding to sequences of bits to resist interferences. So you're going to send 2 useful bits and combination with 1 repeat bit that is going to allow you to lose some of those 3 bits and still understand what is being sent. So the result is that the data bit per symbol is about 5,600. Why do we care? Why do we care? The reason why we care is that there is a secret in transmission, is that the people who designed 802.11ac are, of course, at the IEEE, but they don't work for the IEEE. Nobody worked for the IEEE apart from staff. The designers of the protocols are actually engineers, mostly working in companies designing chipsets, cards, systems, etc. So they don't only have a view of the protocol from a theoretical standpoint, but also have an engineering view of what it takes to design and then build those systems. And one limitation we know of is that encoding is cheap from a processing standpoint. Going through the scrambler, etc., all the process we saw together is pretty cheap and simple on the processing consumption standpoint. But decoding is much more complex because you're receiving a wave. You have to separate the special streams from one another. Then you have to interpret what you have left to see how many bits you lost in each of those symbols, and then use the complementary techniques to try to recombine the missing bits from the bits that are still left there. Then you have to go back the chain, remove this redundancy bit, then go through the scrambler in the back to finally get back to your data. So all that process, interpreting the signal to go back to the original data, is much more CPU intensive and process intensive than coding it to send it away. And the 802.11 designers thought that the maximum performance that we could expect from a single unit of encoding decoding engine would be around 600 megabit per second. So they set a hard limit to say that we should not expect to have any requirement to decode more than 600 megabit per second. But if you look at 802.11ac, there are many of these MCSs that actually are way beyond 600 megabit per second. So what happens when we do? Well, if you have more than 600 megabit per second requirements, you just add another encoder decoder. So for each unit of 600 megabit per second, you're just going to add one more encoder decoder. And this is where it gets complicated, because the reasoning then is to say, alright, so how many decoder encoders do I need? Well, the logic is to say you need a certain number of encoders in one direction, from inside to the outside when you want to send a frame, and then you need the same amount of decoder on the other direction when you receive bits and you want to retrieve the bits inside to get back to your data. And where it's complicated is that when you go from inside to the outside, you start from the data bits, and then you send something which is going to be encoded bits, more bits. And when you work from the other way around, you work the other direction, so you start from the encoded bits, and what you have in the end in the output is the data bits. So the logic is to say that this process should be consuming the same amount of resources. So if you take the MCS data bit per symbol or the encoded bit per symbol, you should be able to divide those symbols by a certain number of encoders and find an integer, say a number of encoders. So the math is a little bit complicated because when you want to make this determination, you're going to take the modulation, number of special streams, and transmission size channels to understand how many bits you're going to have on the data bit side and on the encoded bit side to try to find the same numbers as what you have in this table, for example. And then you're going to divide those by 600 megabit per second to see how many encoders that gives you. By the way, those data bit per symbols and encoded bit by symbol is something you see in the 802.11 protocol. For example, here, this is the 802.11 2012 edition, so that's a protocol you can find on free download. And if you look at the modulation for the section 18, which is 802.11a, you see that they give you some modulation information where they give you the coded bit per symbol and then the data bit per symbol. So you see, typically we call that CBPS and DBPS. And then of course the matching data rate that you get from there. So that's something you find for 11ac, but that's also something that you find for the other protocols. Alright, so again, why do we care? Well, we care because for the MCSs to be easy to compute, the reasoning is that you should be able to take the data bit per symbol or encoded bit per symbol and divide it by 600 megabit per second, and that should give you an integer number of encoders or decoders. This is a problem we didn't have before with 11N and A and G because none of them were having speeds that were approaching 600 megabit per second except for 11N for special streams, but nobody had implemented it yet anyway, and we would just reach the ceiling at that time. But for 11AC, we do exceed that ceiling, so we have to do that math. Okay, so that's nice, but what happens if you take your number of data bits or encoded bits, you divide it by 600 and you find something weird, like 3.05, not something integer, but a number with an ugly face? Is it the end of the world? Well, it's not the end of the world, but we have a problem. And the problem is that you have to use a certain number of encoders, and then you have a few bits left, and you cannot just ignore them, you have to process them. So you need one more encoder, but that encoder or decoder is going to do not much. And an encoder-decoder cannot do not much. It works or it doesn't work. No, it does something or not. So if you have a 3.05 encoder requirement, you have to use 4 encoders, but one of your encoders or decoder will be only dealing with this 0.5 percentage, which is not very much. And that might create some imbalance between your encoders or decoders. So what should we do then? One idea was to say, well, what we could do is when we have those weird numbers, 3.05, we can just say that for those MCSs in the transmission, you will have more than the 3/4 repeat rate or something. You will add a few more bits, and those bits will be used as padding so that you fall back on your 600 megabit per second round number amount of encoders or decoders. So you won't have 3.05 in that case. We'll carve the protocol so that it goes to 3 or it goes to 4. We add the bits that we need so that the last encoder will be fully busy like the others. But you understand that this is a stupid idea. They've designed a protocol that was aiming at being more efficient, and the last thing we want to do is to add useless bits to a transmission just to fit an encoding or decoding requirement. So that idea went away. Instead, they said, well, when we have those MCSs that don't look right because they are not full numbers of encoders or decoders, we're just going to drop them. We're not going to be wasting resources in the silicon doing 0.05%. That's pointless. So if it doesn't fall right to a certain integer number of encoders or decoders, then we'll just drop that MCS from the table, not valid. And you see it coming, right? So they took all the MCSs described in the protocol, and if you have 802.11ac with the CBPS and DBPS, you can do the math yourself, knowing the modulation, and you'll see that those are just not rounded up. They're just not the right number of encoders or decoders, and that's why they were dropped from the table. The thing is that if you look at that list, from a list standpoint, it looks like a long list. So that's a bit concerning because that's a lot of MCSs. And if you put it on the table format, it's even worse because it looks like this. And what you see is that, of course, the more special streams you are sending, the larger your channel, the more complex the signal, with more special streams and larger bandwidth, the more chances you have that it doesn't fall right into an integer number of encoders or decoders. So you have many more not valid MCSs when you communicate at 160 MHz or 80 MHz than you have when you communicate at 20 or 40. And you have many more invalid MCSs when you communicate with more special streams than when you communicate with a few special streams. And that is of course a problem because although today in 2016 we don't have a lot of transmissions at 160 MHz and we don't have a lot of systems that are even planning on doing more than 4 special streams, we know that those will come one day. And those systems will be more efficient than the ones we have today, and yet they will have more MCSs that will be not valid. So that's a concern. You are improving the technology by adding new systems that are more efficient, and you discard some speeds from those systems just because they are not mathematically right. So that is a problem. So they thought about it again, and they said, okay, we are going to make some assumptions. The first one is that if you get to a level where you're going to design 7 special streams, well, very likely you will also want to be able to do 8 special streams at that time. That's one thing. So for every 7 special streams MCS that you allow, you're also going to allow the same transmission with 8 special streams. But what if it doesn't fall into my 600 rule? Well, then you will just have an encoder decoder will be doing not much, 0.05 something maybe, but it will be doing its job because we want to be able to offer those rates. And the second logic is to say if you go to the complexity of implementing more than 4 spatial streams, most likely you will also go through the complexity of implementing 256 QAM. Although these are not related, but they are optional new techniques that were brought by 802.11ac, and the logic is to say any vendor that would be implementing one and going through the burden of engineering a design and making a system that does 4 spatial stream is probably going to also go through the burden of making sure that 256 QAM is supported on their chipset as well. It's not much more of a stretch when you do one to the other as well. So we're going to say that for every modulation that is allowed at more than 4 spatial streams, that modulation should also be allowed if it is using 256 QAM and more than 4 spatial streams. And here again, we have quite a few cases where the result is that you have a non-integer number of encoders, decoders, but that's okay. You're going to have that last encoder doing not much, but we'll want to support those streams. So the result is that we went from the original long list you saw in last slide to only discarding a few MCSs that you see here at the top and the bottom in 2 different formats. So those are MCSs that do not use an integer number of encoders or decoders, and that the 802.11ac group accepted to discard. So again, keep in mind that there are many more that do not actually follow that rule of this integer number of encoder decoders, but those were deemed important enough that we wanted to support them, even though it would not be comfortable from a processing standpoint. But they accepted to drop those, and the reason is primarily because if you look at them, those are likely cases where your system would probably not be privileging those MCSs anyway. So if you look, for example, at the first column, 20 MHz, MCS9. MCS9 is an MCS that you get when you're very close to the access point. And of course, you think if you implement an 802.11ac system and you're very close to the access point, what are the chances that you want to restrict your communication to only 20 MHz? Not very large. Most likely, if you're close to the AP, you have a good signal, you'll probably want to expand to 40, 80 or more megahertz channels, not stay at 20. And if you are in a very high density environment where you have to limit your channel size to 20 MHz, there's not much of a difference between MCS8 and MCS9 in terms of efficiency anyway. So you'll be able to revert back to MCS8 in that case. So we do lose one MCS, but it's not that critical an MCS that it will make a big difference in most deployments. So after weighing carefully all the MCSs and trying to bring back as many as they could into the protocol, they agreed to leave aside those MCSs that were not only not mathematically correct, but also not critical for real-time deployments. And this is why we have these missing MCSs in the 802.11ac table. I hope this was useful for you, and I would like to thank you for watching.